Good afternoon, my name is Fabrizio Ruffini and I will talk about federated learning of explainable artificial intelligence model. As you know, artificial intelligence systems are nowadays in many aspects of our lives, and we want the decision to be trustworthy. For the European Union, trustworthiness is related to some kind of requirements. In particular, for federated learning of explainable models, we are dealing with the necessity to answer simultaneously to requirements of transparency and privacy and data governance. The first part, the federated learning aspect, is related to the privacy and data governance requirement. The idea is that you don't want to share in a scenario where you have different data owners, you want to share raw data to not violate data privacy issues, but you want to have a global model. So the idea is to share the parameters of the models learned locally to have some entity to aggregate these kind of parameters to have a federated learned model. For the explainability aspect, we want our AI system to be explainable to the stakeholder concerned. And so this can be achieved by two generically said strategies. One strategy is to use directly from the start AI models that are designed to be inherently understandable. And in this case, the explanation is in the model itself. Or after the model has taken his decision, you can apply some post-hoc methods, techniques such as feature importance, to explain the decision that has been taken. And so for the feature importance, what is the most important feature that is important for that particular decision? In this context, we have different challenges. For example, we want a balance between numerical performance and explainability, but also we have to deal with the distribution of the data in the client, different clients. In our activities, we used as a case study an AI system for the health sector that is meant to predict the progression severity of the Parkinson disease using a dataset available online. Our first focus is the comparison between the numerical performance of an interpreted by design model and an opaque model that are namely the Takashi-Sukeno-Kang fuzzy rule-based system and a multi-layer perceptron neural network model in two different kinds of scenario, one identical and independent distributed and one non-ID scenario. If we look at the results, we can see that for both MLP and Takashi-Sukeno-Kang systems, the federated learned models are able to achieve better performance with respect to the local learned model. And this is particularly true for the scenario 2, where there is the distribution that change in different clients. Also, we can see that the MLP and the TSK reach comparable distributions, comparable numerical performances, but they have different kind of explanations and different kind of explainability level. And this is the focus number 2. So when we talk about local explanation, we talk about local or global explanation. Local is when you want to explain a single individual prediction. For the TSK model, the explanation is simply given by the rule activated by that input, that in our case is in a simple form because it's a simple first-degree polynomial. For the MLP explanation, you need the post-hoc technique. We choose to apply the sharp post-hoc method that by construction is additive, and so we are able to evaluate the feature importance for each client for an individual prediction, and then make the average for all the clients to have a federated an explanation valid at the federated level. For the global explanation, this means that you want to have some kind of insight of the explanation of on all a data set. And this can be done for the opaque case, calculating the Shapley values for all the individual instances of the dataset, and then make an average. In this way, you have an average and insight of the global feature importance. For the TSK system, in general, for interpreter by design models, global insights are given by the complexity, the structure of the system, number of rules, number of parameters. So to have something to compare between the two models, we decided to use a proxy for feature importance, the average of the absolute values of the coefficients of the linear models in the rule base. Looking at the comparison, we need to say that direct comparison is not possible because two models can achieve the same performance, but with different strategies. And so the direct comparison is not fair. But we can do a qualitative comparison. For example, we can look at the global interpretability for the TSK and the global explanation for the MLP, and we see that the most important feature for the explanation is the age in both cases, and the less important feature is test time in both cases. And this means that somehow the model agrees, the two models agree that the more important and less important are the same features. We also need to say that the computational communication cost is higher for the Shapley values calculation with respect to don't do the calculation in the TSK model. For the forthcoming research, there is a growing interest on the streaming in the FL context, where the data can be potentially affected by concept drift. That is, for different clients, you can have different distribution, but also for different time chunks, you can have different distribution. And we want, of course, an effective global model that is able to be explainable and have good performance at federated level. These are described in these activities and in this reference, and I wish you a good time at this conference.